Welcome back to TEC 293. This is the second video for Thursday, January 21st, and in this video we're going to talk about Lab 2. Lab 2 is a springs lab, and it's a lot of fun because it's just a lot of fun to play with springs. They're kind of like slinkies. It's just kind of addicting. There's something addicting about playing with springs. It's why slinkies are so popular. But there's actually a really good reason why we are going to do a lab on springs. It may not seem obvious. You might be saying, why are we doing a lab on springs in TEC 293? The reason is because springs are really, really good at demonstrating elastic deformation. Remember, we've talked already about elastic and plastic deformation. Elastic deformation is temporary, so when I stretch it and then I release the force, it springs back, right? Whereas plastic deformation, which I don't really want to demonstrate, would be if I pulled it so hard that I stretched it out that it's not going to come back to its original shape. So eventually that's what happens to most slinkies, right? I mean, I have 4 kids. I know what happens to slinkies over time. Eventually the kids stretch them out, they bend them, they undergo plastic deformation, and then the slinky doesn't come back to its original shape. But the point is that every object that you can imagine behaves like a spring to a certain extent, because every single object has an elastic deformation region. Even something that's really brittle, like say a ceramic mug or something like that. Here's my coffee mug. It's ceramic. Ceramics are really brittle in general, which means that they have a very, very small elastic deformation region. Usually, if they deform very much, they're going to break. They're going to shatter. All right, but even ceramics have a very small elastic deformation region, which means that you can cause them to deform a little bit, and if you let that force go, if you release the force, it'll go back to its original shape. Most objects, like metals and polymers and things like that, and woods, they have a much larger elastic deformation region than ceramics do. But the point is that everything has some small amount of elastic deformation that can be applied to it, and it'll spring back. All right. So that's why we're going to do a springs lab, because it's a good way to visualize elastic deformation. And it turns out that every single material that you can imagine behaves like that to a certain extent, up until the point where you start giving it plastic deformation. All right, and we'll talk about that point where you stop getting elastic deformation and start getting plastic deformation. That's called the yield stress, and we'll talk about that later. But for right now, I just want you to know that there's a region where you get elastic deformation, and then if you keep pushing or pulling harder than that, you keep on deforming it, eventually you'll get plastic deformation, which is not going to come back. You're not going to get that deformation back. All right, so that's the motivation. That's why we do Lab 2 in TEC 293. So how are we going to do this? Well, we're going to go through the procedure in just a minute, but I'm going to just show it to you qualitatively first. What we're going to do is use a spring, of course, and I've got a bunch of different springs. I've got 15 or 20 different springs down in the lab that I'll choose from, but I'll choose 2 different springs. I'll try to choose springs that are a little bit different, so it'll be a little bit more entertaining, so they won't be identical springs. Obviously, we'll need a couple of these, and we're also going to need some different masses. So I've got a whole bunch of these. These are the masses that we're going to apply to stretch the spring. And then we're going to need something to put those masses in. So we'll use a pail like this. And then we are going to attach this pail to the spring. And then we need something to hold this spring so it is stationary, at least at one end. So what we're going to use is a threaded dowel rod. I've got that kind of set up right here already. So I think I'm just going to do it right here in my office. I think that'll work just fine. So what we need to do is have this threaded rod. Hopefully I've got enough weight back here. The books are providing enough weight so that this threaded rod's not going to move, so it's stationary. And then we're going to take a spring, and we're going to put the spring on that threaded rod. And then we need to attach the pail to the spring. So in this case, this spring has a little hook on it, so I could just attach it really easily, just like this. That'll actually work. But not all the springs have that, so I've actually got a carabiner. I got a bunch of carabiners that I can use. So I can just clip one end to the pail, and then clip the other end to the spring. Of course, before we do that, we need to measure the mass of the pail and the carabiner, because now we are applying a certain amount of mass, the mass of the pail and the carabiner. So we'll want to measure that mass in addition to the mass of all these weights. All right. So we've got a certain small amount of mass that has been applied so far. And then what we want to do, I skipped a step. Before we even put the spring on there, what we need to do is measure the unstretched length. Here, I got another spring right here I'm going to demonstrate it with. Here's another spring. What we're going to do before we even set it up like that, we're going to measure the unstretched length, specifically the length of the coil section. So that is from right here to right there, because we're going to assume that this section right here and this section right here, they don't stretch. Is that a good assumption? Well, it's a reasonable assumption. It's not perfect, but it's reasonable enough. So we're going to assume that all of the stretch of the spring happens between here and here, from here to here. That's the way the spring is designed to work. So we're going to assume that it's working that way. So first, before we even set up the experiment, we are going to measure the unstretched length of the coil section of the spring. Then we're going to set up the experiment like that, and then we're going to start adding masses, like this one. And of course, we already have measured the mass of these things, so we know how much mass is in there. And once we've added a mass, then we will take something to measure with, a measuring stick or a ruler or something, and we will measure the new stretched length of the coil section of the spring from right here to right there. So now we know how much mass has been applied, and therefore we can get how much force, remember, because we can convert between mass and force. It's pretty easy, because on the surface of Earth, 1 pound mass gives us 1 pound force. So it's pretty easy as long as we're on Earth. All right, so basically then we'll just keep doing that a couple of different times. We'll keep adding mass to the pail, and hopefully that doesn't all come crashing down. Yeah, looks good. So we'll keep doing that a couple more times, and each time we'll keep track of how much mass is being applied total to the spring, and then we'll measure and we'll see what the new stretched length of the spring is. So in a nutshell, that's what we're going to do. We want to get this relationship. We want to understand this relationship between how much force is being applied to the spring and how much it is stretching. All right, so that's what we're trying to get at. All right, so that's the qualitative description. Now let's flip over to the lab manual. It starts on page 19 of the lab manual. So go ahead and pull out your lab manual, flip to page 19, and let's talk through this using the document camera. All right, here is lab 2 on page 19 of the lab manual. We've already talked about why we're going to do lab 2, and we've already talked about what equipment we're going to use to do lab 2, so we'll skip over that. Let's go ahead and talk about the procedure, because I did kind of demonstrate that, but I kind of went out of order a little bit. So I'm going to be careful, because springs pose a pinch hazard, so I'm going to be careful in handling them, and I'm going to wear safety glasses, even though that's a little bit silly. And in my office, I'm still going to wear safety glasses, even though I'm pretty sure I'm not going to need them. But it says to wear them, and that's good safety practice. So what we're going to do is fasten the top of the spring to the support rod, and we're going to measure the unstretched length of the coil section of the spring. Remember, that is the length of the spring from right here to right here. That's the part that's going to stretch. So that's the unstretched length of the spring. And then we're going to use the scale in the lab. We're going to use that to measure the mass of the bucket, as well as the carabiner if we use carabiners. And then we'll hang them from the bottom end of the spring. So now we know how much mass is being applied to the spring. And then we're going to look at it, and if the spring is visibly stretched, then we can use that as our first data point. So if it has, then we'll go ahead and we'll measure the new length of the spring section of the spring, the coil section of the spring. If it hasn't stretched, then we'll keep on adding weights until it does begin to visibly stretch. And then we can record our first data point by noting how much mass is in there, how much mass is applied to the spring, and how much it has deformed elastically. All right, then we're going to continue doing that. We want to get about 4 or 5 total data points. That'll make for a nice plot and give us a good trend line. So we'll do that about 4 or 5 different times, and I'll call out the data, and you will record all the data as we're talking through it. And then we're going to do it for another spring. So we're going to do this for 2 different springs, and I'll try to pick out 2 kind of different springs just to make it interesting. And then we'll put everything away. All right, so once we have done that, then what are you going to do for the results? Well, first of all, I want you to show a table that has all the raw experimentally attained data. And what that means is the length of the spring section. And that would be, show me in that table, show me what the unstretched length of the spring section is, and show me the stretched length of the spring section with each of the masses applied. So I want to see, data point 1 has how much mass and what is the stretched length of the spring. So for each data point, what's the length of the spring section, the total length of the spring section, and what is the mass of the weights that have been added. We're going to measure it in grams. You can't see that. We're going to measure it in grams just because that's what the scale spits out. But I don't really care what units you use. If you want to convert that to kilograms, that's fine as well. But the raw data is the amount of mass that has been applied to the spring. Okay, then we can do the conversion from mass data, measured in grams or kilograms is fine, to pounds force. All right, and we can do that conversion. It's very easy because we're on the surface of Earth. And as long as we're on the surface of Earth, then 1 pound of mass equals 453.6 grams. And sorry, that is actually true no matter where you are. But this next part is only true on the surface of Earth. So this next part, 1 pound mass gives 1 pound of force on the surface of Earth. So what you're going to have to do for each data point, convert the total mass applied to the spring into pounds mass, and then you can convert easily from pounds mass to pounds force because it's just 1 to 1 as long as we're on the surface of Earth. Okay. All right, then what I want us to do is I want you to calculate the change in length of the spring for each data point. So you can do that because we had the unstretched length of the spring like this, and then we're applying a certain amount of force to it, and we're stretching it. And so now what I want you to get at is the change in length, because the force is proportional to the change in length, as you'll see in just a minute. All right, so now in the table, I want you to show the load in pounds force that is applied to the spring for each data point compared to the change, that's the delta x, that's the change in length, that's the stretched length minus the unstretched length of the spring for each data point. All right, so this is not the total length of the spring, it's the change in length of the spring from the stretched length to the unstretched length. All right, so you want to do this for all the data points and for both of the springs that you tested. And then this is kind of some information about springs. It's good to know. And what we come up with is something called the spring constant. And the spring constant is K in this equation. And the higher the value of K, the more difficult it is to stretch. So the more force that has to be applied for a given amount of stretch, the higher the value of K, the higher the spring constant. And the general form of the spring equation, this is also called something called Hooke's law, H-O-O-K-E, Hooke's law, named after the scientist that developed it, I suppose. This is the equation. This is the idealized equation for an ideal spring. In the real world, there are some, it's not going to look quite this pretty, but for an ideal spring, the force that is being exerted by the spring is equal to negative K, K is the spring constant, and X is the change in length. All right, so the question that usually comes up is, why is there a negative sign right there? And the reason there's a negative sign right there is because this equation is from the perspective of the spring. All right, so if I have my spring and then I exert a force this way, then the spring is trying to restore itself in the other direction. It's trying to pull itself back in the other direction. So if I apply a force this way and I say that this direction is positive x, so I'm applying a force in this direction, then the force that is created by the spring is in the opposite direction. It's trying to pull itself together that way. All right, I think that's kind of intuitive. Once you realize that this force is from the perspective of the spring, it's the amount of force being exerted by the spring, not on the spring. Okay. All right, so that pretty much covers that. And here's an example. So if a spring constant, if it's known to be 2 pounds force per inch, then how much force is exerted by the spring when it is stretched by 4 inches? Well, it's pretty easy. It's just plug and chug. F equals negative kx. That's Hooke's law. So negative sign times 2 pounds force per inch times 4 inches. That's the stretch. So your inches cancel out there, and you're left with negative 2 times 4 pound force. So that's negative 8 pounds force. That's how much force is being exerted by the spring. All right, this next paragraph is to explain the way I want you to plot this data. So if we think about the way that we collected this data, the way we collected this data was we had our spring, and we applied a certain amount of mass or a certain amount of force once you do the conversion. So you apply a certain amount of force, and then as a result, you get a deformation, right? And you can measure the amount of deformation or the change in length. All right, so the way that we did this experiment and collected this data, which is the independent variable and which is the dependent variable? Well, if you think about the way we did this experiment, the independent variable, that is the way that we are controlling this experiment, the independent variable was the amount of force that we are applying. All right, so in this experiment, the independent variable was the amount of force that we were applying, and the dependent variable, that is the resulting variable, was the stretch in the spring. All right, so that's really the way we did this experiment. However, I'm going to make you do a little modification here because every other lab that we do in this class follows a standard pattern. And in fact, all of the field of materials testing generally follows a pattern that is actually the opposite of the way that we collected the data in this lab. All right. So we know that if we apply a certain amount of force, we're going to get a certain amount of extension. All right. But we also know that if we apply a certain amount of extension, if I just say I'm going to stretch this by 2 inches, I'm going to get a certain force, right? So you can think about it in either way. Either way is equally valid. You could say I'm going to exert a certain force and I'm going to get a certain extension as a result. Or you could say I am going to stretch it by 2 inches and I'm going to measure the force that results from that stretch, all right? And as it turns out, the whole field of materials testing is almost always done in that latter way of thinking about it. So we apply a certain amount of stretch to the material, and we measure the amount of force that the material exerts on it, on us, on the load cell of the universal testing machine. All right. So all that really matters, I hope that makes sense, but all that really matters for us in this lab, this is the way we actually captured the data. We had the independent variable, and by convention, the independent variable is on the horizontal axis and the dependent variable is on the vertical axis. So the way that we really did this experiment is we applied a certain amount of load as the independent variable, and we measured the amount of stretch as the dependent variable. But what I want you to do for lab 2, it's the only lab that you'll have to do this for, because every other lab is done the opposite way. That's the standard way of doing materials testing. I want you to flip the axes. So what was on the vertical axis, I want you to put on the horizontal axis. And what was on the horizontal axis, I want you to put on the vertical axis. It's pretty easy. Just make sure when you plot it in Excel, just make sure that your stretch is selected as the horizontal axis, the X values, and make sure that your load or pounds force is selected as your vertical axis or the y values. All right, so once you've done that, probably in Excel is the way you probably want to do that. Then I want you to make a trend line. It's pretty easy. Just right-click on the graph and then click Add a Trend Line. And I want you to make sure that it adds the equation to the graph. So you'll see an equation kind of like this on the graph. And it should be a linear trend line. You can kind of see this red dashed line here. That's kind of sort of what your trend line might look like. And the equation for the trend line should be something like y equals mx plus b. All right, let's go ahead and go on to the discussion questions. So in complete sentences, answer all these for both springs that we tested. We'll have spring 1 and spring 2. Number 1, do your data points lie on a straight line? So you'll have a trend line, a linear trend line by that point. Do they all lie exactly on the trend line? If we're really lucky, maybe they will, but more than likely they probably will not, most likely just due to experimental error and measurement error. You know, I might not be able to measure it as precisely as we might like, so probably they're not, and probably it's due to experimental error. Okay, then the next couple of questions. Number 2 says, what is the slope of the best fit linear trend line for the data points? So that's really easy. If you got this trend line and you got the equation right here, the slope of this line is given by m. The slope of y equals mx plus b. The slope is just m. And for number 2, all it's asking for is the numerical value, no units, just m. So you need to answer this in complete sentences, but all it's asking for is a number for each spring, of course. And each spring will have a different value of m. Okay, then number 3 says, what is the spring constant? And as it turns out, the spring constant is equal to the slope of this line. And the slope is given by m, but when we apply this to be a spring constant, we need to include the units. So what are the units for the slope of this line? Well, it's rise over run. The rise units are pounds force, and the run units are inches. So the units for spring constant is pounds force per inch, which kind of makes sense. It's like, how many pounds force did you have to apply to get it to stretch per inch? So the units are pounds force per inch for spring constant. All right, so really, the numerical value for number 3 is the same as the numerical value for number 2. You just have units here for number 3. Number 4, does the linear best fit line cross through the origin? So does this line cross through the origin? Maybe, it might, but it might not. And the reason that it might not is because if you play around with a spring, you'll probably notice that in order to get it to start to stretch, you actually have to apply a certain amount of force to get it to start to stretch at all. I could apply a small amount of force and not get any stretch of the spring. There's a certain amount of force I have to apply before I get any kind of stretch at all in the spring. And the reason for that is because there are residual stresses manufactured into the spring because the designers of the spring want to make sure it comes back to its original starting position. If it didn't require any significant force to get it to start to stretch, then it might not come all the way back to its starting position. So there are some residual stresses built into this coil, and because of that, it makes it come back to its original starting position, but it also means that you have to apply a certain amount of force before you start to get any measurable stretch of the spring. So more than likely, it will not cross through the origin. And then number 5 and number 6 are very similar. Do these for both springs, and based on these findings, how much force would it be required to cause the spring to deflect 1.5 inches? Well, there's actually 3 different ways of doing this, and they're all correct. There's 3 different ways of doing this. So one way would be to say, all right, 1.5 inches. I'm going to go to my plot, and let's say here's my plot, and let's say this is the data that I get from my plot. It's This is made up data, so this is not the same data that we're going to get next time. But let's just say it is. So 1.5 inches is about there, and then draw a vertical line up, and then you can draw a horizontal line over, and you could say that's the amount of force that I would have to apply to get 1.5 inches of stretch. That's one way of doing it. Another way of doing it, probably the best way of doing it, is to plug it into this equation. This is the best fit trend line equation for your data. And so what you're trying to find is y, that's the amount of force, and m is the spring constant, and x is the stretch, so it's going to be 1.5 inches in this case, and b is whatever the y-intercept is right here. If b equals 0, then there is no y-intercept, and this line goes through the origin. But if b does not equal 0, then it didn't pass through the origin. So anyway, probably the best way of answering number 5 and number 6 is to plug in 1.5 inches or 3 inches into these equations for x. All right. And I said there were 3 ways. The third way is probably the least accurate, and that is to use Hooke's law. So this is the spring equation, and you can plug in 1.5 inches for x and plug in your value for the spring constant, and you can find your F. The reason that's probably the least accurate is because there's no y-intercept here. So this is an idealized equation, and it is assuming that there is no y-intercept. So that would only really be true if there were no residual stresses built into the spring that cause you to have to exert some amount of force before it actually gets to stretch at all. But any of those 3 ways are all technically correct, so you could answer number 5 and number 6 in any of those 3 ways and be correct. Just make sure you answer in complete sentences, explain what you're doing, show the equation to explain what you're doing and explain it, and do it for both springs. All right. That wraps up the discussion of what we're going to do for Lab 2 next week. If you have any questions, let me know. You can also come to office hours. That's today, Thursday, from 11 to 12. So that'd be a good time to ask any questions as well. If not, you can always ask me by email is fine as well. So that's going to be it for this week. And I hope you have a great weekend, and I'll see you next week.